Yeah, thank you for inviting me here today to talk about sort of the LIGO and gravitational wave experience about using Pegasus in the last years. So my talk is going to be about how we've used Pegasus to find colliding black holes in the data taken from the LIGO and Virgo gravitational wave observatories. I'm Harry. I'm a faculty at the University of Portsmouth, although I've worked with Duncan Brown, who you sort of introduced earlier on in the last 10 years as well. Just to kind of give an overview as to what I'm going to be speaking about. So I'll just give an overview then of what I want to be talking about. I'll start with a little bit of the theory and the sort of background to the problem. So what are gravitational waves? Why are they interesting? Why is this something that we've invested this money into? I'll then sort of try and address the computational problem. What is the reason that we need Pegasus in the first place, and what are we trying to solve? I'll then talk a little bit about how we actually integrate with Pegasus and use it to help us address the type of computational problems that we have. And then I'll go back a little bit to the science again and just spend a little bit of time talking about some of the highlights of what we've learned from gravitational wave observations in the last 5 years. Now, I could probably talk quite a bit more about any of these points, so if anyone does want to sort of follow up with any of this, either in the chat or Slack or anything like that, please let us know. A couple of my colleagues are on as well today, so I guess they can help answer questions as well as needed. So just to kind of, I'm not sure I get that out of the way, oh, well, whatever. Yeah, just to kind of give a little bit of background then. So Einstein's theory of general relativity in the early 20th century really redefined how we understand gravity and what it is. He sort of posed gravity no longer as a force, but as a warping of space and time, so that we're not, he sort of said, you're not gravitationally attracted, you're not being pulled towards the sun. We're kind of moving in a straight line. It's just that straight line kind of moves on a curved path in this weird picture of gravity as geometry that he came up with. Now this was one of the sort of perhaps two revolutionary theories of physics that came about in the earliest 20th century, the other one being quantum mechanics. But this did predict a number of different behaviors, different ways that things would move compared to Newtonian gravity that preceded this. And one of the main predictions was that the bending of light as it passed near to the sun, and also the variation of Mercury's orbit, both of which sort of agree very well with his prediction. But there was one other aspect of his theory that Einstein himself was never entirely convinced existed, or whether it was just some sort of a thing that came out of the mathematics, and if you rephrase this in a different way, maybe it would go away. But it turns out that this is a very physical effect, this idea of gravitational waves. It's something that isn't present in our Newtonian picture of gravity at all. This idea that wave-like fluctuations of gravity that can travel at the speed of light, these almost fluctuations in underlying space-time itself. And these gravitational waves can be shown to be emitted by accelerating masses if there's some sort of spherical asymmetry. So a star spinning doesn't emit gravitational waves unless it's ellipsoidal. But two black holes, for example, are really a perfect candidate for the type of system that can emit gravitational waves. Now, these are difficult to observe. All particles are affected by a gravitational wave going by. So it's not like if you want to study electromagnetic charge, you take a particle that's not charged and watch how it'll move relative to other things. All particles will be affected by a gravitational wave going by. And a passing wave sort of causes a deformation in a ring of particles, like the illustration you can see here on the slide, that as the gravitational wave goes by, this sort of ring stretches and squeezes in accordance to the wave going by. And this is what we try to observe. The problem is that this interaction between gravitational waves and matter is extremely weak. So if I was to show this at scale, there's no way my monitor could possibly display it, and it would just look like a ring. In effect, the deformation is equivalent to being able to measure the distance to the nearest star with an error less than the width of a human hair. So extremely high precision instruments are needed to try to observe these gravitational waves. And over the last 40 years, people have been envisaging, designing, and building the instruments that have been needed to make these first observations. And here are some of the large-scale instruments that are used today to observe gravitational waves. We can see here on the left the two LIGO observatories in Hanford, Washington, and Livingston, Louisiana. I don't know why I put WA. And also the Virgo instrument there on the right, which is situated near Pisa in Italy. The two LIGO instruments are 4 kilometers long. So the distance, I hope you can see my mouse, from here where the base station is to here at the end of the arm is 4 kilometers. This one's actually situated on one of the old Manhattan test sites, so a good use for land that's really unusable otherwise. This one's situated in a swamp in Louisiana. This one's actually situated on farmland, so somewhat more used here. But these large-scale instruments, using an interferometric technique, you sort of shine the laser up. You shine lasers up both arms and time how long it takes for the light to get back. And if there's this ever so slight squeezing and stretching, it'll take a little bit longer to get up one arm than the other. And we can use an idea called interferometry to measure the effect of the gravitational wave passage. And this has then allowed us to get to the point now where gravitational wave observations have become possible, where we have reached the sensitivities needed. So sort of changing gear a little bit now, moving from this to the computational problem. These observatories produce a time series, something like what we might see here. In fact, this is real data from the observatories. This time series contains a lot of noise from instrumental sources, both seismic noise, shock noise, laser noise, etc., but might also contain buried within there gravitational wave signals. Now, for many of our sources, we know what we're looking for. People have managed to solve the problem of how to numerically evolve two black holes through a collision and can create a signal for predicting what the gravitational wave emission would look like. So we know what our data is, we can understand it and characterize it, and we know what we're looking for in terms of the gravitational wave signal. So the problem becomes sort of how to combine these two things together, our input, what we're looking for, and the data that we have to find gravitational waves and sort of write the PRL, which led to the Nobel Prize in I think it was 2017 now. Luckily, this is a problem that's existed for quite some time and has a reasonably well understood solution. The idea here being that of match filtering, that if you understand the character of your noise, if you understand the various noise sources in play and can figure out sensitivity as a function of frequency, and you know what you're looking for by producing these template waveforms, and you have obviously the data, you can combine them together, feed it through this sort of mathematical machinery, and you can produce something like this, a signal to noise ratio time series, where here you have time on the x-axis and signal to noise ratio on the y-axis. And Gaussian noise should sort of look somewhere like this in the sort of small region. And if you get something that's a genuine gravitational wave signal in here, you should get a large spike. All of this data is actual data from the first gravitational wave observation, and there's a URL there if you want to use our toolkit to reproduce this plot. It is made directly from that example. So then the question becomes one of, okay, we sort of have the tools in play. How do we plug all of this together to sort of consider this in terms of a workflow? The dominant issue here is that we have to search over hundreds of thousands of these template waveforms, and we have to search at all times to try to find gravitational waves. And that's what kind of makes this expensive. When we add in a little bit of extra complexity due to some things that I don't have too much time to sort of go over in detail, it sort of gives us the following basic workflow, that we have a lot of pre-processing jobs, take a little bit of wall time, but not much total CPU cost, normally better done on your local compute site. Then we have a whole host of expensive jobs that are doing this match filtering. And these are embarrassingly parallel, and they're at least 95%, if not more, of the total compute cost. But there might be tens of thousands of these jobs in a typical workflow. Each of these are sort of designed to run maybe 4 to 12 hours. This is then followed by a lot of post-processing jobs, and that can take maybe a day of wall clock, but not so easy to parallelize and doesn't run on a huge number of cores. Can also come with high memory requirements. And that sort of branches out quite a lot. We kind of have this tree of post-processing stuff that sits there at the end. And this is a sort of nice example then to pull all this together into our workflow machinery. A sort of more detailed image of this, thanks to some folks I worked with a few years ago, just giving a little bit more detail about how all the post-processing stuff goes in. All of the stuff in these boxes here is the various post-processing steps, and the computationally expensive thing just sits here. So to sort of explain then how we've interfaced with Pegasus, I'll talk a little bit about PyCBC, which is also what I'm wearing today. So PyCBC is one of the main analysis codes within LIGO and Virgo used for observing the collision of black holes. It's also used extensively by groups outside of the collaborations and includes some of our key contributors, including one of the people in attendance today. It contains modules, functions, utilities, programs to address a number of the problems in the analysis and characterization of merging black holes, but finding them is arguably still the main purpose. It's fully open source, GitHub, PyCondor, or whatever, and you can go to pycbc.org to sort of see some documentation and tutorials. This replaced an earlier C-based toolkit, which did have a bit of Python in it, that was used during the early 2000s called LALAPS. And this was a project that began from Duncan Brown's group out of Syracuse, but with the number of us who have now moved on, today most of the main developers are based in Europe, so there has been quite a shift, and increasingly we've got a user base in India that's growing rapidly as well. So we've sort of moved quite a bit towards the Europe-India direction over the last 5 or 6 years now. PyCBC first started using Pegasus around 2012. It replaced a custom Python written Condor Dagman API that we had used in the past for writing workflows. We heavily subclassed what is now deprecated Pegasus 4 DAX API in what's called the PyCBC workflow module. We are working to adapt this now to work with Pegasus 5 and see what of that subclassing is now not needed. That's work in progress. All of our LIGO compute centers, although it's not true for Virgo, use Condor, and so this sort of fits well with our local running, where we just want to build, in most cases, building workflows that can work efficiently on our local compute centers is always useful. But recently, there's been a strong shift towards OSG. So we've used OSG extensively in recent years to access resources for doing this expensive match filtering step. And this combination has observed and published more than 50 colliding black holes and will continue to do so. So just to sort of give some of the science highlights, here's a results plot that appeared in the gravitational wave first detection PRL. What this plot is showing, without going into the details, is that we have observed gravitational waves with a 5 sigma detection. It produced the headline statement that's in the abstract. And this is a plot that was produced in a Pegasus-powered workflow from within the collaborations from the PyCBC toolkit. As of today, we've observed around 50 binary black hole mergers. Somehow I seem to not have updated the plot as I intended. So there's a lot more than what we show here, but this is kind of starting to really tell us the population of black holes in the universe. How heavy are the types of things that form from the collapse of very heavy stars? We're now beginning to ask questions like, is there preferences in the angular momenta that these objects have? Is the mass distribution perhaps being bimodal, which might suggest a couple of different formation mechanisms? We are really now starting to get into some of the deeper astronomy questions behind this and not just trying to make the first detections. And finally, a sort of the last science highlight that I'll highlight was in 2017, we made the first observation of 2 neutron stars, which are objects that are almost heavy enough to become a black hole, but not quite. Now, because these still have some matter in play, as they collide, they effectively rip apart, emitting a lot of radiation throughout the electromagnetic spectrum. And we simultaneously observed this both with the LIGO and Virgo observatories, but also with the Fermi Gamma Ray Observatory. This enabled us to figure out where on the sky this object come from, and within 11 hours, people were observing an electromagnetic afterglow from this event, which was is now probably the most observed source on the sky in human history, I think, at this point. So gearing back in then from some of the science highlights to the questions that you posed for us. I think I'll sort of read through this, but my top level thing is, I think I'm echoing what Patrick said quite a lot, but maybe I'll come at it from our perspective. The most common thing I heard, and I did ask some of our users as well for some feedback here as well, and a common thing, our workflows contain about 100,000 jobs on average. The dashboard for monitoring this is a really useful tool. However, in maybe as many as 5% of workflows, the monitoring process fails or lags behind, and then we don't get accurate information. And we don't know that that's happened. So if a user's using this and isn't experienced, they won't know, which unfortunately means that we can't use the dashboard because we can never be sure that we're not in that 1 or 2, 5% of time when this has happened. So this sort of results in us never using Pegasus Analyzer or the dashboard, and always using Pegasus Status as the one tool that we know gives us reliable and up-to-date information. And it's sort of related to this, I quote one of our users, "I want the dashboard to take me to an actual Python traceback easier and faster." So if we can solve the reliability issue, how do we quickly, we're not, either a workflow is running fine and you see that. If it is failing, you need to be getting to that Python traceback and seeing what's going on. Patrick was talking about trawling through some of the log directories. We symlink the Condor log directories, and we turn off the subdirectory management that Pegasus does by default so that we can more easily get to those error and output files. But it is a regular thing that I have to look there. I think, I mean, we sort of touched on it. Most of our development teams now in European or Indian time zones. This can make collaboration difficult, but I don't see an easy solution for that. We're not going to move half the people around the world to solve that, but it is something maybe to think about. The sort of HPC thing again, some of us now have access to Slurm or similar clusters locally. We haven't yet figured out how to get one of our workflows to do this, which is partly always finding it easier to run on the Condor OSG stuff anyway. But it would be great if there was a simple example where if you have access to a Slurm cluster, or maybe you can set up a Condor head node, how would you get that interaction working? We don't really know where to start on that, and I don't think anyone's had the time to dig properly into that. But it does mean that there's often resources that we're not using that we have locally. And then finally, we are still porting our code to Pegasus 5. We do have some technical request issues that are coming from this, some of which we fed back already. But I think at this point, it's a little premature while we're still in doing that development process. So I think we probably need a bit more work on our end before discussing sort of that translation at the end of the day. And yeah, thank you all for listening. I hope that was interesting.